Hello, so I will be talking about Lab 5, and I've chosen to discuss the scenario of the following slinky. And first of all, I'm going to introduce the lab and its purpose and the system and surroundings in our case. Then I'm going to be talking about the essential equations and formulas which we're going to need for the code. And then we're going to be discussing the observed data from the video and the tracker, and then we're going to be analyzing our code, and then we're going to finish off by dissecting the discussion questions. And so, what is the purpose of this lab? So, we'd like to analyze the aspects of our system, which is the slinky, and we're going to be analyzing the motion of it falling down, and through which we're going to determine the effects of the two forces acting on it, which are gravity and drag force. And we're going to use that information to then predict the motion of the slinky. And for this, we're going to be using the fundamental principles, which are Newton's second law, weight force, and drag force. Here are the equations of the three formulas we're going to be using. And the Newton's second law, which we have used in, if not most of our labs, all of our labs. And so this is the video. The mass of the slinky is 0.218 kilograms. We've used this guy as our reference for the height, and this is the initial position of the slinky. So we're here, and then the initial velocity is 0 because it starts from rest. So this is our code in the initial conditions. So we know that out from the video that our spring mass is 0.218 kilograms. We've plugged that here, and then this is the initial position, which we have computed, which we have observed from the video, sorry. And then the initial velocity is 0. As we said, it starts from rest. This is the drag proportionality constant, which we need to plug in our formula for the drag force. And so the code is going to be separated into two loops. The first loop, while the bottom of the slinky is still constant, while it's still stationary, where the net force is 0 because it's stationary. And the second loop will be when the slinky is falling down, thus then it's not constant anymore. And so in our code, this is the tension force. This is also the gravitational force. The tension force is the opposite of the gravitational force, as they're canceling each other, causing the net force to be 0. As the slinky is stationary, the net force is 0, as we said. And then this is our velocity update. This is pretty much simple. It just updates at the current position the velocity of the slinky and then the position. And so our second loop is when the slinky is already falling down, because it's not stationary anymore. And that means the net force is not 0 anymore, which means the drag force then is applied. And it's pretty much the force of the air resistance. And we can see here this is our formula for gravitational force, and this is our formula for the drag force. And if we initially look here, this is the formula for the drag force, the constant, the velocity to the power of 2. And it's simply plugged into the code. And then these two once again will be used to update our velocity and position at the current moment. And so what we get from the tracker and the code are these two values. And the blue line represents the code of what the code produces. And it's pretty accurate. It pretty accurately reflects on what happens in real life. However, there can be errors, as there could be external forces like wind acting on the slinky, which could cause some fluctuations. And then another error could be obviously human error, which could be inaccurately placing the point to track the object. And so let's discuss, why does the bottom of the slinky remain stationary? So the forces in the y direction cancel out, causing the net force to become 0 because the tension force is acting in the opposite direction but has the same magnitude as the weight force. And the slinky is pretty much like a big string when you think about it, so it counteracts with the force of tension. And what if we put a large weight at the bottom? Would it remain stationary? So it could, it depends. It will remain stationary if we have a long slinky, which is long enough, or has a spring constant, which is also large, so the tension force could equal the gravitational force. And then the weight rate will remain stationary until the top of the spring reaches it. So the idea here is to make sure we have a net force of 0 to have the slinky remain stationary. And thank you for your attention.